Good afternoon, everyone. My project is AI for safe and efficient robot path planning using formal methods for indoor navigation. Funny thing about this project is that the day I was offered this project, I went to my internship where I have been writing about AI agents, compliance, saving GPU costs and everything. And something pretty hilarious happened. You might think that's why I chose this project, but no. Um, while rushing to the office, I ran into a glass door. So the glass door, which was supposed to open automatically, didn't open that day. And that opened up my brow. I went to my professor, and the project suddenly made a lot of sense. So I chose it. So when we talk about the glass door problem, it kind of highlights one problem that is kind of common in a lot of robots right now. A lot of robots are used to indoor spaces that are static. But however, if we are to bring them into our workspace, into our work dynamics, they need to be prone to dynamic changes. People are moving, doors are opening or closing, floors might be wet, something like that could happen, and robots must be respectful to these contextual replannings. So it's tempting to use GPT-like stuff for this, but this is all very black box, so you would like to have some formal methods that can verify and actually show you why a decision was made. So that brings us to the project that I'm going to be working on, where we are using mission inputs that are translated by LLMs into real rules, which then combined with existing scene graph understanding methods like SLAM creates a dual heuristic planning, which will learn from existing logic and what it's learning real time in the dynamic environment to share among robots and finally reach a successful state. So I'll just talk a bit about SLAM. What is SLAM? So SLAM is how robots move nowadays. It's simultaneous localization and mapping. In this, the red, yellow, and green paths are the paths that a robot takes in multiple passes, while the gray cloud at the bottom is a LiDAR-based map that is being made by these robots as it's looking at it. So again, as I mentioned, there are problems with it. It is usually done with a centralized learning, meaning a lot of robots are sending their data to one point, which creates a point of failure. It contains a lot of static world assumptions. It's not refactoring for a lot of dynamic changes again and again, which is pretty common in these Amazon warehouse videos that you see. And it is already being used over there. And that's because no human is driving a crane through it. And there is no representation for uncertainty, as I mentioned. So to do that, I kind of want to talk about what our project already is. My professor is already working on something called Swamp Slam, which is a decentralized way of doing this. Here you can see 3 robots that have been left independent in a parking space. And these robots were on their own able to communicate with each other and map the space around it to create this map that was made in low latency and very low Wi-Fi coverage, and simply by sharing what is changing from their passes, between their passes. Sorry, the clock. So that brings to me the open challenges that we are trying to target for our PhD. It's basically creating a decentralized way for these robots to talk among each other. As I said, using key changes that are happening in the environment around them. We'll use probabilistic planning to handle uncertainty in dynamic environments. That means that the robot, instead of some strict solid rules, will be able to handle dynamic planning. And finally, all this will be done using a dual heuristic planning, which will be training on our own data set as we go. This kind of explaining the dual heuristic planner a bit, but basically it will create a loop where if the action designed by the heuristic is not correct, it's going to run through the runtime check and again and again until it's successful. So that's how it should look like. You have the human instruction, which is being translated into a logic and actually leads to a robot plan. And that's pretty much it.